doing. Okay. So if anyone has any questions, feel free to speak up and interrupt. No need to put it on the chat. So today's talk will be about proving Fermat's last theorem for n equals to 4. The general case is hard, everyone knows that. The proof is around 200 pages, so you can take an entire semester of seminars on the general case. The n equal to 4 case uses a technique called infinite descent. So infinite descent is a type of proof by contradiction where we assume that the proposition is indeed true, and then we show that that assumption leads to some nonsense. And the nonsense here is that if we assume there are solutions to Fermat's last theorem with n equal to 4, then there must be a solution strictly smaller than this solution. But this leads to an infinite chain of smaller solutions, which is not possible because there is a smallest natural number. So our assumption that it is solvable in the first place must be incorrect. So this is the statement for Fermat's last theorem: a power n plus b power n is c power n. So in today's talk I will be doing it for n equals to 4, which is the only easy case. And turns out this was proved by Fermat himself, and this is the only proof that has survived from Fermat. And Fermat was actually a lawyer, not a mathematician. He was a professional lawyer, and he did mathematics in his spare time for fun. So to prove that there are no solutions for a power 4 plus b power 4 is equal to c power 4, we will prove something slightly harder, slightly stronger. We prove that there are no solutions to a power 4 plus b power 4 equal to c square. If there are no solutions to 2, then certainly there are no solutions to 1, because c power 4 is c square whole square. To show this, we first make a few observations. The first observation is that it is sufficient if we look at the case when a and b are co-prime. Because if a and b are not co-prime and they have some non-trivial GCD G, you can divide throughout the equation by the GCD to get solutions to the equation that are indeed co-prime. So we'll only talk about solutions that are co-prime, and since they are co-prime, a and b cannot both be even, because this would mean that their GCD is 2. And and the third observation is that both of them cannot be odd, because if a is odd, it is either congruent to 1 mod 4 or 3 mod 4. In both the cases, a power 4 will be congruent to 1 mod 4. Similarly, b power 4 is also congruent to 1 mod 4, and their sum is congruent to 2 mod 4. But observe that the right hand side is a perfect square, and perfect squares are always congruent to either 0 or 1 mod 4. Thus, but the left hand side is true, therefore both of them cannot be odd. One has to be odd and one has to be even. Without loss of generality, say that a is even and b is odd. Now observe that a square whole square plus b square whole square equal to c square forms a Pythagorean triplet, and because we assume that a and b are co-prime, this is also a primitive Pythagorean triplet, which means that there must be numbers m and n such that we can rewrite a square, b square and c in terms of m and n as follows: a square can be written as 2mn, b square can be written as m square minus n square, and c square can be written as m square plus n square. And a square can only be 2mn because we have assumed that a is even, so it forces b to be m square minus n square. So now, because we have assumed that b is odd, this forces n to be even here, because we can rewrite this equation as m square equal to b square plus n square, and again this forms a Pythagorean triplet. Therefore we must be able to rewrite b as x square minus y square, m as x square plus y square, and n as 2xy. And since we have assumed that a is even and b is odd, this forces n to be even and take the value 2xy. Now now observe that m from equation number 1, a square equal to 2mn, we can rewrite a by 2 whole square as m times n by 2. Now the right hand side is a perfect square and m and n both are co-prime, therefore m and n by 2 themselves must be squares. Now from equation number 6, which was n equal to 2xy, we can rewrite n by 2 is x and y, and we just observed from rewriting equation 1 that n by 2 is a perfect square, and since x and y are co-prime, x and y themselves must be again perfect squares, therefore x is of the form u square and y is of the form v square. And from here, from equation 9, m is of the form w square. Now we substitute x equal to u square, y equal to v square, and m equal to w square into equation 8, which was m equals to x square plus y square. Therefore we have w square equals u square plus v square, which is a strictly smaller solution to the equation than our original a square whole square plus b square whole square equal to c square, thus establishing an infinite chain, which is not possible since there is the smallest natural number. Thus we have reached the contradiction, therefore this equation must be unsolvable. Is everyone with me so far? Does anyone have any questions? Feel free to speak up.
No, we're following you.
Okay. So this was the first proof for Fermat's theorem. Now there is an alternative proof for Fermat's theorem. So we do all this analysis here, not mathematical analysis in the everyday sense, that one of them that both cannot be even, both cannot be odd, they must be co-prime, and one must be even and one must be odd. From there we have a different proof without using Pythagorean triplets, and this proof is as follows. So from equation 2 we have a power 4 plus b power 4 is c square, where a is even and b is odd. Now we rewrite this equation as a power 4 is c square minus b power 4, and from elementary algebra this can be rewritten as c minus b square times c plus b square. Now we make a few observations again. The first observation is that there is no odd prime that divides both c minus b square and c plus b square. So to see why this must be true, assume that there is an odd prime p that divides both c minus b square and c plus b square, then it must also divide their sum, which is 2c, and because p is odd it cannot divide 2 but it divides 2c, therefore it divides c. Now similarly it also divides their difference, therefore it also divides 2b square. Again, because p is odd it cannot divide 2, it must divide b square. And by Euclid's lemma, because p divides b square, p also divides b, therefore p is dividing b and p is also dividing c, therefore p will also divide c square minus b power 4, which is a power 4. But this means that p divides b and p also divides a, but we assume that a and b are co-prime, therefore this is a contradiction. Hence there is no odd prime that divides both c minus b square and c plus b square. Now the next observation we make is that both of them cannot be even. This is because we have a as even and b as odd. This forces c to be odd, therefore difference of c with b square and sum of c with b square both must be even. Now the claim is that their GCD is 2. To see, so we have already shown that there are no odd primes in the GCD and both of them are even, so GCD must be some power of 2. To see why it is exactly 2 and not some higher power, observe that 4 does not divide both c minus b square and c plus b square at the same time. This is because say arbitrarily say 4 is dividing c plus b square, and we have assumed that b is odd, therefore b square is congruent to 1 mod 4, and because 4 divides c plus b square, this makes c congruent to minus 1 mod 4. Now look at their difference, their difference will be, look at their difference in mod 4. C is -1 and B is 1. -1 is -2. So 4 is not dividing C minus B square. Similarly, if 4 divides C minus B square, C will not divide C plus B square. It can only divide one of them. Therefore, this means that the GCD is exactly 2. Using these three facts, we rewrite C minus B square and C plus B square as 2x power 4 or 8x power 4. To see why it must be 2 and 8, observe that on the left hand side we have a power 4, therefore whatever is occurring on the right hand side must have 2 to the power of 4, because both of them are even. But 4 cannot divide both, so 8 must be in one and the remaining 2 must be in the other factor. So C minus B square is 2x power 4, where x is an odd integer, because again, if x is even, their GCD will be greater than 4. And C plus B square is 8y power 4, where y is coprime to x, because otherwise the GCD will again be greater than 2. Or it might be the other way around. C minus B square can be 8y power 4 and C plus B square can be 2x power 4. Now the claim is that the first case is impossible. To see why the first case is impossible, look at their difference. Their difference is 2b square, which is minus x, 2b square, which is minus 2x power 4 plus 8y power 4. But this forces x square to be congruent to -1 mod 4. But there is no number x whose square is congruent to -1 mod 4. All numbers have their squares congruent to 0, congruent to 1 mod 4. Therefore, first case is impossible. It must be that we are in case 2, that is C plus B square is 2x power 4 and C minus B square is 8y power 4. Did I mess it up? Oops, looks like I messed up my slides. C minus B square is, oh no, it's alright, okay. So C plus B square is 2x power 4 and C minus B square is of the form 8y power 4, where x and y are coprime and x is an odd integer. Now observe that we can rewrite b square as x power 4 minus 4y power 4. This means that 4y power 4 is again of the form x square plus b and x square minus b. And the argument that we used here, that there are no odd primes dividing both of them, there are no even, both of them are even, and 4 divides both of them. From the same argument, it must be that GCD of x plus b square and x square plus b and x square minus b must be 2. Therefore, x square minus b is of the form 2c power 4 and x square plus b is of the form 2d power 4. This means that their sum is of the form x square. Their sum is of the form x square equals c power 4 plus d power 4, which is a strictly smaller solution to the equation than our original a power 4 plus b power 4 equals c power 4. I messed it up again. This must be a different variable. We have already used c. It's the same u and v. See, x square is u power 4 and y square. Think of c as v and d as u. X square is u power 4 and d and u power 4 plus v power 4, which is a strictly smaller solution than the original solution. Therefore, this establishes an infinite descent, which is impossible again, since there is the smallest natural number. Therefore, there cannot be any solutions to the equation. So this is the summary of the technique. We assume that there is some solution exists, and we are showing that if this solution exists, then there must be a strictly smaller solution that also exists. This establishes an infinite chain, which is impossible because there is the smallest natural number. That's it. Does anyone have any questions? Anything that I should go over again?
Oh yeah, proving this for quintic equations would be hard.
Proving this for what?
Power 5 equation.
Yeah, this is the only
That is
easy
Fermat.
case.
Okay, so that's why you took power 4 equation.
Yeah, power 5 is more complicated. Everything other than 4 is more complicated. Even 3 is harder than 4.
Even 3. Oh,
Yeah.
why 3? Why is 3 harder than?
I don't know. I haven't looked at the proof, but it uses some algebraic number theory. It uses some field theory.
Oh, probably check that out, but I'm
Yeah.
harder than.
4 is the only trivial case. I think 3 was proved by Euler.
Oh, so basically now you're saying I can extend this method to quintic, but then I'll have to use other theories to incorporate properly.
Yeah, some other techniques.
Okay, so this one alone won't be enough to prove the This
Yeah.
one alone won't be enough to complete.
Actually, Fermat's the theorem is that for any n greater than 2, it doesn't hold. That's
Yeah, it
what he
doesn't
conjectured.
Hmm.
For 4, he himself proved it, and for the rest, he wrote it in the margin saying this margin
I know,
is yeah.
it's too small to
Yeah.
for the proof to fit in.
So this is also called Fermat's infinite descent.
Yeah, but wasn't there a general proof for all such a
Yeah,
for
there-
3?
Yeah, there is a general proof. The general proof was by Andrew Wiles,
Yeah, 200
Wiles.
page or something.
Yeah, it uses heavy algebraic number theory. We can give seminars.
I can't understand.
Yeah, I don't understand it either. Lots of machinery going on there. We can give seminars for one full semester on that
Yeah,
on that
I mean,
proof.
keeping up with even the power 4 proof just with screen share and audio was kind of hard. I think I'll have to try going through the video again. You have recorded it.
Yeah, it's recorded.
Can you please post on the YouTube channel?
Yeah, I will.
Do this again and try it on.
I will. Any other questions? Okay, then I'll stop the recording and then we can have a general extended discussion.